Going to talk about capacitance and capacitors. So, also we are going to discuss why capacitors are very important and how do we use it in our everyday lives, particularly in our electronic devices. Before understanding capacitance, we need to understand also that capacitors are materials that has the ability of having a capacitance. But what is really capacitance? Capacitance, by definition, is the amount of electric charges that are being stored inside the capacitor. Of course, it is based on the amount of electric charges is stored in the capacitor is based on by what amount of electric potential is being applied to the capacitor. So meaning a capacitors are materials that stores electric charges. And if a capacitor stores electric charges, then the output of it would be a capacitance. Again, by definition, capacitance is the total amount of electric charges that is being stored inside the capacitor. Now, capacitance is defined mathematically also as the amount of electric charges present with respect to the voltage applied or the potential difference applied in the capacitor in which allows the capacitor to store electric charges. And of course, it is also defined as the area of the conducting plate. Okay? And with respect to the distance between two conducting plates. Now, capacitors are materials that is composed of two kinds of materials that we are going to use: conductors and insulators. And then later on, we will discuss also, we'll revisit what makes a capacitor. But first is we need to understand first mathematically also the different variables present in capacitance. Now, there are two equations that we can use. Equation 1, which is the capacitance charge equation, and the capacitor that is based on the conducting plate. Now, there are different letters that we can associate with this equation. We have capital C. Now, the symbol C will denote as capacitance, but the unit of capacitance is in farads or capital F in honor of Sir Michael Faraday. We also have a potential difference of V with the unit of volts. The charge is represented by Q with the unit in coulombs. And of course, we have epsilon naught or the permittivity of free space, which is a constant number, which is equal to 8.85 times 10 to the negative 12 coulomb square per Newton meter square. And of course, the surface area of the conducting plate, which is in meter square or square meter. And of course, the distance d between two conducting plates, which is in meters. Now, there are three kinds or types of capacitors, and there are different examples of capacitors. The most famous one are parallel plate capacitors. So, what are the different components of a capacitor is that we have two conducting plates and a dielectric. So later on, we will also define what is a dielectric and what are conducting plates. Now, conducting plates, do we need two conducting plates? One, a positive plate which is attached to a wire, and the other one is a negative conducting plate which is also attached to a wire. And these two plates has a certain surface area. They should be equal in size and in area. Now, of course, since there are two conducting plates as illustrated here in our diagram, the they have different sign conventions, a positive and a negative. So what happens here is that the electric charges will will move from a higher potential to a lower potential. In that particular sense, there would be no capacitance or electric charges stored uh, because of the electric field present, the strong electric field present. Now, the other type of capacitor is a cylindrical one, so it's in a form of cylinder, and the other one is a sphere. But the most famous ones are parallel plate capacitors and cylindrical capacitors. Now, these are the different examples of capacitors that is based on the dielectric material used in the capacitor. We have an electrolytic capacitor, we have a mica capacitor, we have paper capacitors, films, film capacitor, non-polarized capacitor, and ceramic. Now, in every capacitor, there are two poles, or there are two leads. The longer one and the shorter one. As you have this, I believe this was discussed in the robotics class, but the longer one will denote that this is the positive terminal of the capacitor, and the shorter one is the negative pole or the negative lead of your capacitor. Okay? But there are some capacitors that has no polarization LEDs or polarized LEDs, such as a non-polarized capacitor. So non-polarized, these two LEDs are not polarized. They are not uh, they don't have a negative and positive terminal. But there are instances that we need to understand also that we need to place these capacitors in our circuit in the correct manner. And how do we use and how do we see that one? Say for example, in unpolarized capacitor, this must we have arrows as our guide, wherein this end should be connected on a certain end, and this end will be connected to a certain end. Of course, in polarized capacitors, the positive terminal should be attached in the positive if if we uh, if we connect capacitors in a series connection, then we can do it in series manner, and we can also do it also in a parallel connection. Now, to further understand capacitance, I would like to share this simulator on capacitance, because what we need to understand how electric charges are being stored inside the conducting plates. I have here a simulation of a parallel plate capacitor. Now remember, there are no this is the two conducting plates. The present are two conducting plates of the capacitor, and the two plates has an area of 200 millimeters square. And I have here a battery connected to the two plates so that we can collect or we can store electric charges. And capacitance, as defined, is the amount of electric charges present with respect to the amount of potential energy or electric potential applied to the two capacitors. So we have here the positive side of the battery and the negative end of the battery, which are connected also to two plates. So this manner, the two plates are not yet connected to the battery. Now, the total capacitance of these two is equal to 0.3 picofarads. Okay? Now let's try to see if let's connect let's connect the wire to the battery. So let's say for example, if we apply 1.5 volts, if we apply 1.5 volts The positive charges will be collected by the positive plate. So the assuming from a 0, 1, 0, no potential difference or electric potential is applied to the plate. There are no electric charges yet on the plate. So we have here the plate doesn't have any stored material or stored electric charge yet. Right? So we have here 0.5 picocoulombs. Now why picofarads? Because 1 farad is a very huge number, and electric charges are very small. They are so small that we cannot see it in our own naked eyes. So they are even 1 coulomb is very large, is very big already. So sometimes we use suffixes centi to pico to femto to note that these are the amount of electric charges present due to the small amount or due to the size of the particle also. If we apply, so notice that there are no electric charges on the plate yet. They are separated at a certain distance, 6 millimeters, in a square surface area of 200 millimeters square. If we apply 1.5 volts, so, so from 0, as we increase to 1.5 volts, and this kind of manner, so let's measure by how much is being stored. So that's around 0.25 volts yet still. So if we increase, so there are a total charge of 0.07 picocoulombs present. So if we increase into 1.5, so the conducting plate receives 1.5 volts. Hence, the total amount of charge in the plate is equal to 0.44 picocoulombs. Hence, the capacitance is equal to 0.3 picofarad. So if we use the charge, the capacitance charge equation, if we divide 0.44 picocoulombs with 1.5 volts, that will give us 0.3 picofarads. Now, what would happen? What would happen if we decrease the separation or the distance between two plates? So uh, from 6, say, from 7, uh, from 6 millimeters, we decrease it by a factor of 2. Say we have 2 millimeters. The capacitance increased. The capacitance increased. If the capacitance is increasing, the number of electric charges also is increasing. Now this means that whenever we increase if we decrease the distance between two conducting plates, the capacitance will increase, because in our equation, in the equation that we have, which is C is equal to epsilon naught, multiply it by surface area all over R, the distance is inversely proportional with the capacitance. So if we decrease the distance between two conducting plates, the capacitance will increase. But if we increase the distance between two capaciting plates, the capacitance decreases. And if we increase the distance of the plates, the charge also decreases. But if we increase the plates, if we increase the plates or decrease the distance of the plates, the charge is also increasing. Now, what happens if we increase the area? If we increase the area of the plates, the capacitance and the charge also increases. And so on and so forth. Now, I have mentioned that this the there is a space between these two, so there is an electric field present. Yes, there is an electric field present in our system, and this electric field is always present because there are two conducting plates of different convention. Okay? So this is how capacitors work without dielectric material yet. Now later on we will discover, as we will discuss also, what would happen to the capacitance of the material if there is a dielectric present in the system. Now let's put the equation to the test. So I have here two problems. Let me read each of the problem. There are two conductors with a net charge of 10 microcoulombs and negative 10 microcoulombs. So there are two plates with separate charges. Since it is always necessary that the two plates are identical with each other, with the potential difference of 10 volts between the two of them. Now, we need to determine the capacitance of the system. And the second problem is how much charge is collected on each plate of a 4 microfarad capacitor when it is connected to a 12-volt battery. And if the capacitor is connected to a 1.5 volt battery, how much charge is stored in the capacitor? Now let's revisit first problem number 1. Now remember 1 microfarad or 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. Now, we use the capacitance charge equation. Why? Because in the given problem, we have a charge of 10 microcoulombs and 10 volts. So that would suffice equation number 1. C is equal to Q all over V. But the question is, there are two charges present. Positive 10 microcoulombs and negative 10 microcoulombs. Which of is it choose? We're going to use the positive one. They are identical. Right? And it is dependent on the positive one. Okay. So we have here 10. So if we substitute Q with 10 times 10 to the negative 6, if we convert 10 microcoulombs, or 10 microcoulombs to coulombs, we have 10 times 10 to the negative 6 coulombs divided by the amount of electric potential exerted to the capacitor or the conducting plate, which is 10 volts. Okay, that will give us, so if we divide the two, we get the ratio. We'll have a capacitance of 1 times 10 to the negative 6 farads. Or we can simply write this as 1 microfarad. Okay? Now, let's go to the second problem. The second problem tells us that if we have a 4 microfarad capacitor, how much electric charges or how much electric charge are stored if we connect it to a 12-volt battery. And if we connect it to a 1.5-volt battery. Now, we still use the same equation, capacitance charge equation, which is C is equal to QV, and substitute the given variables. So we have a charge of 4 times 10 to the negative 6 because that's uh, we have a certain value. We have here 4 microfarad is connected to a 12-volt battery. Okay, so never mind this one. Okay, never mind this one. Uh, this should be this the correct process is shown here. So I made a boo boo here. So this is the correct process. So we have here a capacitance of 4.0 times 10 to the negative 6. That's 4 microfarads is equal to Q. Okay, is equal to Q all over, assuming it's connected to a 1.5 battery. So all over 1.5. Now what we want to do is the Q would stay on this side of the equation. Right? This would stay on the side of this side of the equation. What we can do here is we can multiply both sides with 1.5. If we multiply both sides with 1.5, we will have 4 times 10 to the negative 6 farads times 1.5 volts. And that would give us 6 microcoulombs. Now, what about if it's connected to a 12-volt battery? Now, let me show you how it is being done manually. Now, what I use here in my solution is the FeeWiz app. So, let us show using our board. So, if we have a charge, let's write the equation first. C is equal to Q all over V. So we have a capacitance of 4 times 10 microfarads times 10 to the 6 farads, which is equal to an unknown charge Q all over 12 volts. Okay, all over 12 volts. So what I want to do is that we can multiply both sides by 12 volts because I want Q to stay on this side of the equation only. So to that, I need to equalize the equation. By means of equalization, I want to make the equation equal with each other. So what I'm going to do on the other side of the equation, I will also do on the other side of the equation. So 12 volts divided by 12 volts, that will give us 1. Okay? So what is left with our equation is Q is equal to 4 times 10 to the negative 6 farads times 12 volts. And that is equal to, that will give us a value of 4.8 times 10 to the negative 5 coulombs. Okay? So that is 4.8 times 10 to the negative 5 coulombs. Now let's also show it manually. Let's show how a 4 microfarad capacitor is connected to a 1.5 volt battery. So we use the same process. we have here 4 microfarad, which is equal to 4 times 10 to the negative 6 farad, is equal to unknown Q all over 1.5 volts. So if we want to let Q stay on the other side of the equation, whatever I do on the side must be done also on the other side. So I will multiply this by 1.5 volts, also on this side by 1.5 volt. If I'm going to do that, this will cancel out because 1.5 divided by itself will give us 1. And that will give charge Q is equal to 4 times 10 to the negative 6 farad times 1.5 volts. That will give us a value of 6 times 10 to the negative 6 coulombs, or 6 microcoulombs. Okay. Are there any questions? If there's none, then that's great. So if you still have questions, you can just write down your questions in the comment and I'm going to answer it. So thank you for joining me in our session on capacitance and capacitors. I'll see you on the next session. Thank you.